All right, it's 4 o'clock, so let's get started. So welcome everyone to lecture 23 of 545. So today we will be talking about imitation learning. So a couple of logistical things. So we are grading homework 3, so we will hopefully get that back to you in about a week or so. Lab 3 has been released and is due coming up soon. So see the Piazza post about the signups for using the physical robot. Lab 4 is also released, so just letting you get a head start on that. If you're like bottlenecked by the physical lab experiments, the lab 3, you can also do lab 4. And we have also released homework 4. So homework 4 is hopefully it's something new this year versus last semester, and hopefully it's not going to be too bad. The entire coding for the behavioral cloning is going to be about 15 to 20 lines long. So you'll just have to put in like 15 to 20 lines of Python code, and then any other coding will be like, I wrote up some Python script for plotting, basically. And yeah, we will cover the details of that in this lecture. So if you want some advice on homework 4, then it's good that you're here. Otherwise, you'll watch in the video recording, and there should not be any technical problems this time. Yep, and then we're making things due April 26th because then you have a few days until the final exam on, I believe it's May 1st. So any logistical questions? Hi. So today is about imitation learning, but imitation learning is also very closely related to reinforcement learning, as you might expect from the name. So I just want to briefly review some of the things that we covered last week in the reinforcement learning lecture, because there is some overlap between the two concepts in terms of where they apply and some assumptions they make. So in reinforcement learning, you might remember that the basic idea is you have some agent. This could be a robot. I mean, sometimes people just call it an agent because it's a generic term. So agent or robot, whatever your term, this thing is going to produce action or control. So that's going to be something that causes it to do something. Like it might be a change in the joint angle or the change in the gripper pose. So those are some common actions that in robotics we have. And then there's an environment. So an environment is, where the robot is. It includes the robot as well as other, objects and obstacles that it faces, and it basically encapsulates, what does the robot have to do. Now the agent or robot will execute an action, and then out comes the next state, as well as a scalar reward signal. So higher reward means it's better. And then the cycle repeats for multiple time steps until some termination condition. Yeah. And these are the basic ideas, and all the learning is based on observed samples of outcomes. So, you have to have the robot, take steps in the environment, see what was good and bad, and then infer, like, what should it do to continue maximizing the expected reward. So last lecture, we also talked about active reinforcement learning. So here the objective was to learn the optimal policy and values. So basically, if you learn what are the values, like the optimal values, then you basically have your policy. So if you remember, when we were able to enumerate all the possible states, we had the state, and then we had different action, and then you could compute what is the value of the agent being at some state and taking some action. And then you have a number for that. And for the policy, if it's at the given state, just do like an argmax, overall possible action, pick the one that is going to lead to the highest Q value or state action value. And remember the difference, before this, we had talked about Markov decision processes. So Markov decision processes involve transition and reward. And if you're doing algorithms like value iteration, that will assume that you know like the definition of what are T and R. In reinforcement learning, as well as imitation learning, we're not going to assume we know that. So the only thing we see is like the outcome. So like, to be clear, it's like we don't have access to like the implementation of R. Like we can't just put in like any value of the state, action, and next state, and then get the number. All we observe is, the agent was here, we did an action, we got to the next state, and then we got a number. Like those are samples. And we also saw that in reinforcement learning, there was a fundamental trade-off between exploration and exploitation. So exploration, you try something new that maybe you don't know if it's good or bad, but you never know until you try it. And if it ends up being better than what you're already doing, you might as well continue using it. And then that way exploration can help the agent find like higher value states in the environment. And again, the learner actually had to take action in the world and find out what happened. So if you remember this example, like when we look at this cartoon, we can tell that if it's going to fall in that fire pit, well, of course it's going to be bad. But again, the agent or the reinforcement learning algorithm doesn't know that. It only knows that until the agent tries it, gets a very negative, it must be negative, I assume, negative reward, and then the feedback from reinforcement learning will make it, assign lower value to the state there. And yeah, we had talked about Markov decision processes. So again, just a brief review. So if you know the Markov decision process, which by know the MDP, what that means is like the definitions of the reward function and the transition probability, then you can compute what are the optimal values and the policy. So the asterisk notation, like the thing that you see here, that means like optimal. And we talked about the technique. Now, if you don't know the MDP, that means you don't know the definitions of the transition probability and the reward function. We talked about model-based solution and model-free solution. So model-based means you approximate those unknown things, and then you do the same technique as if your approximation of the MDP was true. For model free, you just ignore that process of trying to define like transition and reward, and then you just directly do Q learning. And we also talked about model free learning, the idea that the agent will experience the world through episodes. So episodes will have a starting state. So you have your state. It takes some action, gets a reward, gets the next state, the next action, and so on. And that's what all the prime means, or the prime indicate the next time step. But once you get to like 3 or more, then that actually should be 3 primes instead of 4. Which if you're writing out the notation and you have more than like 2 primes, just put in the number as a subscript. Like the state with a 1 as a subscript is like time step 1. And then it's a lot more scalable that way. Yeah. And then we also talked about these being transitions. So that's the state, action, reward, and the next state. And we saw the diagram. So like this circle means that we're at the state F. We have decided to take action A, but we haven't like resolved that. We haven't executed it in the environment. We only do that until we get to this triangle here. So yeah, these are some of the things that we talked about last class. So any questions about the reinforcement learning lecture and review from last time? But we went through the entire class and we covered a lot of things. So I'm happy to answer any clarification that you might have about this. Hi. So why do we care about imitation? Well, one reason is that reinforcement learning has some problems. Can you guess what some of them are? I mean, there's a hint on the slide. I mean, what's the problem with reinforcement learning? Suppose you have a robot that is a caregiving robot. So you're at home, you have a robot that helps to like give you like food or water and help to like clean up something at your home. Would you want like reinforcement learning to happen? What's the problem? Yeah. What? So yeah, I think you're getting at there's less hope for mistakes. But I think there's less room for mistakes, basically. So what will happen with reinforcement learning is that reinforcement learning requires exploration. So that requires the robot to try many different actions that it hasn't seen before. So a robot that is operating like near human, like it doesn't like unless you do something to it, which is then it's not reinforcement learning, but if you're in the vanilla reinforcement learning setting, the algorithm does not really know what is good or bad. So it has to try things. But if it has to do things like explore, it could potentially try very dangerous or risky action that you would not want happening. And so reinforcement learning is often used in simulation environment where you have your like a computer, you can run something, and then the robot is operating in simulation, not the real world. So it's pretty harmless when that happens. And one thing that is an issue philosophically with reinforcement learning is that the robot or the agent will have to do a lot of exploration. But it also feels like for many different tasks, we have a lot of prior knowledge or a lot of data about like what is good or bad. So in autonomous driving, we've collected a lot of data from, well, at least the companies have collected a lot of data. So it seems like we should at least make use of that data. And in other tasks, we'll have other like data or like rules that indicate, what might be good, what might be bad. So it feels like we might want to use that somehow. So that brings us to imitation learning. So imitation learning assumes that we have access to demonstration data. Now, when you look at imitation learning, you'll see that there are many different terms that have been used interchangeably, like demonstrator, expert, teacher, or supervisor. So all these are like synonyms, like they're things that can generate data for you. So like in the homework, for example, we've given you demonstration data, and then basically we have to try to learn from that. Now, we will assume that an optimal policy generates the data, so we can then sample from it. Like now, there's a whole line of work on like imitation learning from suboptimal demonstration, but we're not going to assume that for the class. So here we're just going to assume that the demonstrator is optimal, or at least is good. Yeah. Now the demonstration data will consist of paired states in action. So at state S1, the action that the demonstrator took would be A1, and so on. And then this would be like one episode or maybe a bunch of episodes. In fact, you usually want more than one. I mean, more data is usually better. So, Now, this is state action. Sometimes you'll get observation action. So the distinction is that state is often like the bare minimum of like the most efficient representation of the environment is like a bunch of numbers usually, and then or at least a bunch of statistics about like the robot or the object like poses. And observation is often higher dimensional from sensors that give partial information like a camera that gives you an image. So usually, like if you're dealing with images, you would consider them as observations instead of state information. So now, given the demonstration, the agent must learn from that. So the distinction between imitation learning and reinforcement learning is that in imitation learning, we will not have environment interaction when training, or at least when learning from data, which that's a huge advantage. I mean, this is a very big advantage. So instead of a robot in the real world doing something very risky and exploring, it can just learn, without actually doing anything. It just has data. And then it can sort of understand, like, at these types of states, what is a good action? And it doesn't have to try things out, get a reward, and so on. Now, the agent will still do like environment interaction, but it's going to be at test time. So, in reinforcement learning, there's a training period where the agent must interact with the environment, get the state rewards, and so on. And then you might do some testing. So you might fix the policy and then roll it out in the environment and then get some statistics. You would do the same thing with imitation learning. You roll out the agent in the environment, get some statistics, but you wouldn't have to interact with the environment when the agent is learning from the data. Like that's the distinction. And we're also going to, I mean, the way that imitation learning is studied today is that states and observation, they're often very high dimensional. So last week when we talked about Markov decision processes and reinforcement learning, you could write out the state. So the state S1 has value this, S2 has value that, and so on. But what if the state is continuous? Then it's not clear how to do that. I mean, you can discretize it, like make it discrete, but at some point, discretization is going to be limited, especially when you just get, higher dimensional state. And like, how do you discretize like image observation? It's not clear how to do that beyond like, the images are not technically continuous, like they're discrete in the sense that you have discrete RGB values, but the states are just so, like they're just so many different states that it's not possible for an agent to like experience every one of them. And that's one of the differences between what we studied last week and then what we studied this week. Now, and that's why we will use machine learning techniques to try to like learn some kind of mapping that reasons about that high dimensional data. Now, you can still use machine learning with reinforcement learning. We just didn't cover it. And then, but for imitation learning, we will assume that the state and observations are high dimensional. So do you have any questions about the setup here? All right, imitation learning versus reinforcement learning. So just trying to make the differences more concrete here. So imitation learning, the agent will not interact with the environment while it's learning from the data. It assumes access to demonstration data, which may be a strong assumption. So maybe there's some task that's very difficult for a human to perform. So maybe it's not easy to get that demonstration data, but if it's another task where we have lots of demonstration data, like maybe driving, it might be an easier assumption or a weaker assumption to make. In reinforcement learning, the agent will interact with the environment and get a reward signal, but it does not assume access to demonstration data. Now, again, when we talk about the algorithm, they're not like, it's not the case that, you have an algorithm, it must be imitation learning or reinforcement learning. You can have algorithms that are arguably both. So here's one example. You initialize the policy with imitation learning from some data set, and then you proceed with reinforcement learning. So if this is your method, is that imitation learning or reinforcement learning? Or at least why is that useful? Like why would this be useful? Yeah, yeah. So it would probably, I think you're saying it probably would let the robot avoid dangerous action during reinforcement learning. So I think another way to, I think that that's good. Another way to make it a little more concrete is near the beginning of reinforcement learning training, that's probably when I'm doing the most amount of exploration and thus taking the most high risk action. If you're doing imitation learning to initialize your policy, then it's already going to be kind of good, and then reinforcement learning could make it even better. But the imitation learning will help it avoid that early stage of where it must have high exploration and could be very risky. So when talking about imitation learning, there's a couple of different algorithms that are commonly used. And the most straightforward one, and at least the easiest one to understand, and which is also what you're implementing in the homework, is supervised learning of behavior, or sometimes at least the common term is behavioral cloning. So again, the input is the standard demonstration data that you assume from the problem. And the result after this is a learned function that maps from observation or state to action. And the function can be a neural network, support vector machine, decision tree, and so on. So the exact choice is not too important. Just imagine that it's some kind of function. The input is the observation, you directly make the action at the end. And when you use machine learning, this is an example of using machine learning, especially supervised machine learning. So supervised machine learning means that you have labels for all the inputs. So the labels are action. So if you're familiar with things like, if you've taken a machine learning course, then some of it will be a little bit obvious, but I just want to clarify in case students have not taken a machine learning course. The easiest analogy is, think of like a computer vision task, like image classification. You have an image, you have some function, you produce a vector of probability for each of the image classes. In this case, it's kind of like the same thing, except the output is not like probability for like a class. The output is going to be the action itself. So, the action could be like a vector of the joint angles of the robot. So, many robots have like 7 joint angles. So an example could be a neural network that takes in an image and then produces a 7-dimensional vector of which is directly the action. And again, it is supervised learning because you have label. The expert gave you the label. Yeah, unsupervised means it's harder, but we will not cover that in today. So a very brief machine learning background. So again, just trying to make sure that people have at least a common foundation. So in machine learning, you will learn pattern from data set. So gotten some data set, want to learn something from it. And these days, neural networks have gotten very popular and effective as machine learning models because they can learn to approximate or learn like very complicated patterns, and they get very effective as the data size grows larger. Then we have a lot of good hardware today, like GPU, that can make the training process more efficient. So in behavioral cloning, you would map the observation and state, you would pass it into some neural network and then have it produce an action. There's the notion of a loss function. So a loss function helps to measure how bad a given model is. So the higher the loss, the worse it is. So suppose that the output is discrete. So you have maybe 4 different actions, so like up, down, left, or right. That could be a discrete action space. And then the loss function would be the cross entropy loss. So that measures how close are the distribution between the output vector versus the probability vector that puts in a 1 where the real action is, and 0 in the other component. And if the actions are continuous, like the change in joint angles or like the change in x and y, then you would use mean square error. There are variants of the loss function, but no, these are the most basic ones to be aware of. And backpropagation is the algorithm that is used to train neural networks. It's been among the most widely effective algorithm out there. So it will update neural network parameters, though sometimes we call them weights, and it uses a gradient descent. So we talked about gradient descent a couple of weeks ago, and no, this is basically how it works. I mean, there's some more nuances to this. Like usually there will be a mini batch of data to update by gradient descent instead of like one thing as we covered earlier. But if to think about it, like it's easier, I think, to think about it as like an extension of the gradient descent that we have already talked about. Now, backpropagation too. So again, you don't have to implement it. So you would use libraries. So the company like Meta have put out great libraries like PyTorch to do this. And in PyTorch, you have some loss function and then do loss dot backward, and then that runs the backpropagation. And for more, I think there's some courses that you will see, like, these are not the only ones, though. These are like the master's level machine learning course, so I highly recommend them if you haven't taken them already. All right. Any machine learning question? All right. And so to clarify some of the common notations, so we've already talked about what a state means. We've already talked about action. And then again, the observation we also observations are like the higher dimensional thing, like images, and the state you can think of as something that's lower dimensional that concisely encapsulate all the information that the agent would need to know about the environment. So that's why in this graphical model or BayesNet, we will have this thing pointing to the O1. So it's kind of like the Z that we used earlier in class. It's just a different set of notation, because of historical reasons. And then a policy, if we parameterize the policy with parameters theta, then we would put that notation here, and then that means we have to find what are the good values of this thing here. So when we enumerated the table of these values, like last week when we were enumerating all the states, we didn't have to think about that because you could enumerate all the possible states. We just had a table. But you cannot do that in practical setting where the number of possible observations goes to infinity. And yeah, every time there's some observation, you would pass it into the function. So this is a famous image from a paper that showed a neural network could do a lot of classification tasks very effectively. And this is just a cartoon image showing some action. So the action is not actually an image in almost all cases. It's going to be some like vector of probability or like, the change in joint angle or whatever. Yeah, so this is hopefully just a common set of notation to be aware of. So when we talk about supervised learning of behaviors, this is conceptually how this will work, though. These are some other examples of visualizing it. So one way to do this is you might have a human here. The human is presumably an expert driver. The car, or this looks like a bus, would collect some camera images. The action would record what the human is doing, like moving left or right, or like braking or something. You would put that all in a training data. Then you would run supervised learning to get your policy. And then at test time, you could pass in some image, query your deep neural network. So we didn't put in the A here, but you can also write it as like pi theta of A given O, because it's the distribution of A given the observation. You can put the A there if you want. And then the action maybe turn left or right. Just an example. You could have many other action spaces. All right. And this type of thing, like it dates back to roughly 1989, though, before most of you were born, including me too. So it's one of the oldest test cases studied. You would have some kind of input. And what? This is from a 2011 paper. So, back in those days, you couldn't take an image and then pass it to a neural network. You had to like simplify it to a much smaller thing. And then, yeah, because it was 2011. Okay. And the output would be some number that is a steering angle. All right. So let's look at an example video. So this is from this paper. I mean, you can look at the link if you want. So this is a super tux kart. Have you played that? No one? It's from 2011, so I don't know. But you can kind of see what's going on, right? There's someone controlling I mean, the agent is controlling the car, then it must presumably not fall down. So let's look at the video. All right, sample expert trajectory. I mean, you must have played something like this. Wow, interesting. Huh. So I think what happened is that there's a cube in front of it. The driver must try to get it, I think. And then that must be the finish line. All right. So everyone saw what happened there. Like it drove like the expert, which I think as a human was driving in that game and then got to the finish line. So this is the supervised learning approach. So this is behavioral cloning, like what we had talked about. So very simple algorithm. Here's what happened. Yeah, so when it goes down, I guess the game doesn't try to show that. Like, it'll like pretend that you can drag and drop the agent back in. So what's going on here? Why are they not working very well? Any idea? That was awful. Huh. All right. This is the name of an algorithm in that paper. I think it's a little bit too much for the purpose of this class, so you don't have to worry about it. The more important thing is to know what this means. So at 210, we're going to go here. All right. This is Dagger. Again, when you write Dagger, the second A is capital. So to make sure you write it like capital D-A and then lowercase g-g-e-r. All right. All right, this is Dagger. So this is not a human. This is an algorithm that learned from the data how to drive here. And it's doing a lot better. It's doing a lot better compared to naive supervised learning or behavioral cloning. Although I don't know why you keep avoiding that question mark block. But what about this last bullet point here? Why did it not do so well? Yeah. What?
I don't just like imitate what it's not the data might not always.
Can you say that one more time? Like, I think you mentioned something about.
So the aspect does not penalize the agent for going off track.
All right, so for naive supervised learning, the algorithm does not penalize the agent when it goes off track. That's one way to think about it. We're gonna cover. I think here's how I would describe it. In supervised learning, you can learn the mapping from state to action, but at test time, if there's a very slight error, which can happen in machine learning. Machine learning will always have like some amount of error in learning. Then as soon as the agent goes off track, the distribution of state it experiences is different from the distribution of state in the training data. And then when the training data and the testing data diverge, machine learning is not good. So the core idea is the coverage of the training data distribution. We're going to cover that now. So what went wrong? So if you look at this visual here, there's an expert trajectory that, driving in this environment. Then the learn policy is trajectory with this, different colored dashed line. And what that's going to lead is, that's going to result in different distributions that the learn policy experiences at test time versus what was experienced by the expert. And if you're familiar with machine learning courses, the first thing that people do is you learn how to do supervised learning from non-sequential data. So the data will be like independent, identically distributed from some data set. You'll have like one thing, like one image or one input. But here we're doing sequential decision making. So again, you might still have one image input, but that image is going to be correlated with the prior image, and then the one before that, and then the next image will be very correlated with the current image. And when you have correlated data, it breaks some assumptions that are made in traditional machine learning context, where informally, and I'm glossing over a lot of details here just to make the presentation clear, but in machine learning, you can assume that if your train error is small, then the test error is also going to be small. But that assumes that the train and test data come from the same distribution. So if you're doing image classification, you might have a huge data set from the internet. You can take that data set, randomly draw 10% of them to be in testing, and then the other 90% are in training. And in that case, they come from the same distribution because you drew them from some big distribution and then you made no distinction between, what images should go in train or test. You just randomly sample them like independently. But it's a little bit different when you have a sequential problem. So again, visually, the expert training data distribution will be here, but then the learn policy test time distribution will be somewhere over there. All right, any questions on that? Yeah. So does this mean that supervised learning is bad for sequential decision making? Well, we're going to cover, like, it depends on what you mean by supervised learning. So the algorithm that we're going to cover next, Dagger, is arguably also a supervised learning algorithm. It's just that it will have better coverage of the training data distribution. So I think the answer to your question is, if your training data distribution, even in a sequential decision making, has a lot of coverage, like if the expert trajectory had a lot of coverage in this area, then it might be okay because it gave you what is the action you should take, even if you had a state that seemed a little bit off center. So it's a little bit difficult to give a broad answer. I think with a sequential decision making problem, supervised learning can be good, but the caveat is you must check that the training data has sufficient coverage over what you want the robot or the agent to do at test time. It's all about, is the training data distribution broad enough to cover what you want to do at test time? Like that I think is the bigger point here. So we have this data distribution mismatch, right? We train on expert data, which stayed on track. But if you make a single mistake, you go outside the training data distribution. So you can think of this as an expert trajectory. So a notation that is very common is to use tau. So tau would be A1, like observation 1, action 1, observation 2, action 2, and so on. And don't get that confused with the tau that we're going to cover on Wednesday, which is about like a generalized force. So as long as you're aware of like the context, it should hopefully be clear. You get some expert trajectories, you get some data for supervised learning. This is a common notation, so capital D or in like MathCal font. You get paired observations and action. And then you use that to train the model. And then at test time, what happens? At test time, the agent might be at this state over here, which will be similar to what was in the training data. Now, maybe during training, the expert went to the right, but at test time, the learner made a very slight error, then went off track a little bit. It went to here, like O2 test. Then the problem is there's a very slight divergence. Now we go to the next time step. The problem is if there's another mistake, because it's very often like if you make a mistake, it's easier to make a mistake that makes things worse than makes things better. I mean, it's more things that can go wrong than right. So at state O2 test, you might go to state O3 test and then get even further away from the training data distribution. And the problem is that there's no training data for that recovery. So what's the solution? Well, oh, sorry. The solution is get some expert data here. That's it. That basically is the core idea of Dagger as compared to like supervised learning, which doesn't try to incorporate that logic. Any question on this? Yeah. Uh, so so yeah, are you wondering, is this going to be very data intensive? Like you have to have the expert give you labels for all of this? Well, yeah, I mean, it is going to be data intensive, but I mean, people have to make the judgment call, like, you know, do you have the bandwidth to get expert data here? Then if so, we should do it. If not, then we have to live with like maybe worse or more limited performance of the learned agent. So I mean, there's like trade-offs involved. And then that basically leads to Dagger. And then I think your bullet point here is, of course, this needs a supervisor. So here's what Dagger is. So Dagger stands for dataset aggregation. So again, just make sure that the D and A are both capital. Like when you write in stuff, like it'll auto correct you to lowercase a. So just make sure that it's capital A. So the algorithm is just 4 lines long. I mean, you can write it with 4 lines. In your code for homework 4, you can write all the Dagger stuff in about 4 lines too. I double checked when I coded it up, so hopefully it's not too much work. So for Dagger, you collect training data from the learn policy data distribution. The way you do that is roll out the learn policy, provide corrective labels. Of course, it does need a supervisor. So a common choice of a supervisor is a graduate student. So graduate students often are like working with robots, and then when they have to improve performance, the robot makes a mistake, the grad student has to like correct the robot, and then yeah, maybe it gets better. Yeah, I mean, faculty don't do these things. Like faculty tell the students to do this. All right, and then sometimes you have an algorithm. So in the homework, you actually do have an algorithm. You have a reinforcement learning policy that already tells you what is good or bad. So you can query that. Yeah, so is this always practical? It's a very strong assumption to have that constant supervisor. Maybe it's easier if you have an algorithm, but if you already have an algorithm, then you might as well use that actually. So what this diagram is trying to show is that if if you're at this state here or this observation, and then the learner makes a slight mistake, it goes left. But what happened is during training, it actually saw that state because the learn policy was rolling it out, and then at some given state, the expert is going to correct it to make it go back on track. And the same thing for all the other intermediate, stages in that, red trajectory. So the Dagger algorithm, 4 lines long. So train the policy from the data using behavioral cloning. You run the policy to get the observation. You ask the supervisor to label each observation and the data with some action, and then you aggregate. So that way you're not throwing away old data, you're taking in the new data, then just making it even bigger. And if there's one thing we've learned about machine learning, is that, just increase the data set size and it's probably okay. I mean, how much data ChatGPT trained on, right? All right, let's take about a 5-minute break now, and then yeah, feel free to think about Dagger and ask me some questions about it during the break or maybe after the break. So we'll be back at around 4:55. Well, if you put it in a new racetrack, well, let's say if you put it in a new racetrack, then after the human, you give it a label.
So then you would have to do this for every track.
Sure, yeah. Yeah, the fun thing, this is a very strong assumption to have an expert always available. So the expert will assume that the expert is always available to provide a label to the state that they will understand.
So this only works for environments that is really restricted.
Well, I mean, if it, and that needs a little bit of context. Depending on if the supervisor, the human, or the supervisor, the algorithm, the supervisor, the human, and you train it on some data set, and then you run it to get your policy observations. If you run it on some new, like race color track, you get the observation. If the human is still good enough to give the right people, then it's going to be fine. But again, you need to assume that the human is like there and can give you the. Yeah, that's like a different algorithm, they make different trade-offs and emotion. So that's why there's so many different options.
Just wanted to ask if there's already used in manipulation tasks in present team projects or they already use that. Is it just a theoretical concept? Is it just a theoretical?
I think that I'm not covering them. So we're better than covering the foundation. Also because it's very it's often usually you want to supervisors don't have. Often people the algorithm requires data recognition that is often used to train how we get over the observation. With that tough time, it's hard to assume the information versus observation. That's why. Hmm. All right, so let's get started. And hope your break went well. So again, this is Dagger, and just to make things clear, like this first step, if you're only doing step one, that is like behavioral cloning. So step one is basically your homework 4. And then steps 2, 3, and 4 are like extra credit. They're the Dagger part. So yeah, this is just train on data using supervised learning. And again, the main assumption of Dagger is that you need to have a supervisor available, which is a very strong assumption. Now, the way that Dagger is often used in robotics projects now is that there will be some algorithm in a simulator that assumes access to some low-level state information, which at test time, you don't want the robot to assume. You just want the robot to work with like observational data, like images, instead of state information that it doesn't have. So what a lot of people have done, myself included, is that you use an algorithm on state information, provide labels, but the learning policy will only actually see the observation. So it's a very common tactic and way that I think Dagger is most used in robotics today. All right, so what I wanted to do now is just to give some implementation tips. The main reason is that we don't have like a full-blown lecture on here's a PyTorch tutorial. So I think it's going to be easier if we talk a little bit about some of the low-level implementation tips that people often follow in the type of imitation learning as well as reinforcement learning code today. So again, these are trajectories, so there's sequences of state, action, reward, next state, sometimes with observation instead of state. In fact, in most code, you'll see that they use observation instead of state for the trajectory. Now, in the homework code, we encode this information in a path, right? So this path would be a dictionary with a list of, observation, a list of action, a list of reward, as well as a done criteria. Now, one thing you'll notice is that many times in presentation, we just say, here's the state, action, reward, next state, but we don't talk about the done. So done is like a binary signal that says like, is the agent done at this point or is it not? And that's often it's a very subtle point that is very important when implementing things because sometimes trajectory will terminate early and then you need some way of knowing like is that the end of the trajectory and then the next one. Like if you calculate the reward, you want to make sure that the reward sum up across one trajectory or like one path. So you don't want to mix different paths together. But of course, it's not just enough to have one path because the environments are going to be stochastic. So the agent does something and then something different might happen. And so whenever you run some policy in all but the most trivial cases, you're going to get some different paths when you run out when you run the same policy. And so you want to get a sequence of paths. So you want to have multiple paths, and then the combination of all these paths form the data that is used to train the policy using supervised learning or behavioral cloning, or Dagger as well. And the common interface that people use is based on something that OpenAI developed using the GIM interface. Although, these days people have converted to to the gymnasium, but just in either case, you're going to get a similar API. So this is some environment. So the environment ENV will encapsulate the information that you need to know, like the reward function, what is the transition probability, and so on. And then this action is something that is presumably produced by your policy. You provide it as input to the step function. Now the step function will execute the action in the environment, which in homework 4 will mean you run the simulator, and then you get the next state as well as the obtained reward as a result of taking that step. You get a done criteria, and then sometimes you'll get other information. So the convention is that if you're using Python, you'll run environment.step with some action. You get a tuple of output, and then the last thing is a dictionary that has a whole bunch of arbitrary information that the reinforcement learning or imitation learning algorithm should not need to look at, but you can save a bunch of information in there if you want to do things like plot something or do additional analysis. So yeah, this is the fundamental way that a robot, simulated robot, really is going to interact with environment that someone has come up for you. All right. Any question about the implementation tip? Again, some of you might already be experienced with some of the things. I just want to make sure that for those of you who haven't seen this before, that you have some foundation to build upon. Yeah.
How do we decide what reward the robot should get from probably?
All right. So you're wondering, how do we determine what reward the robot should get? Oh, the environment should give it to you. So when you have code that says environment.step action, it returns the tuple, and then one component is the number, which is the reward. You just get it. So someone has implemented the reward function for you. For homework 4 purposes, the environment has been implemented for you, then you will just get a number. So you don't actually look at the definition of the reward function, although you can try to change it, but reward hacking is very difficult to do and not something I would recommend to do the first time. And we're also doing imitation learning for the homework, so you wouldn't really be doing reinforcement learning. The reward is just something to help evaluate at test time. The number indicating how good the agent did. But the long story short, it's going to be implemented for you. Yeah. So some other implementation tips. So if you're new to PyTorch, then I think the best way to learn something is to actually try it out. So PyTorch is very popular. I mean, it's ridiculously popular. If you're trying to see what libraries are the most popular that people use, PyTorch is one of them. I mean, you can look at the tutorial for more. For the purpose of the homework, you don't need to know things like data loader or transforms or saving and loading models. The homework code will do that for you. Now, data loader and transform, those are often things that are used to help formulate your data set. So if you're dealing with an image-based task, you might be doing classification. And a very common transform that people do is image augmentation. You might, flip the image, you might rotate it. And if you rotate the image a little bit, presumably if you're doing image classification, the class should not change. But you just want to make sure that the neural network is robust to those types of changes. So you can augment the data with transform and stuff to increase the size of your training data. But we are not doing that here. So you don't need to know that. You just like all the data is going to come from environment interaction. It's going to give you observation. And the data that we gave you also includes action. So that's your data. And then you just directly pass it into your neural network. So if you remember the NumPy that we covered, like we had like a NumPy tutorial with Python and ROS. So it followed a similar NumPy interface. Like that's one of the biggest advantages because a lot of people are familiar with NumPy in terms of how do you form an array, how do you do array arithmetic, how do you do like broadcasting and so on. And very often you can do the same operation in NumPy as you do in PyTorch. So you have like two tensors in PyTorch, you can add them together using like the plus sign, the same thing with like NumPy array. And you'll get like the similar numbers, the same number, really. And the real advantage of like PyTorch is that the data is going to be called tensors, where then NumPy they're called like NumPy arrays. And then with PyTorch tensors, you can put them on a GPU. And then that will make things run a lot faster. It better the bigger your data is. So for the homework, putting things on the GPU might actually make things a little bit slower because it's very low dimensional. Like the states are like they're continuous, but they're also like small in dimension. So you don't need a GPU. Like GPU is mainly if you have like a really deep network with lots of data, and the more you have of that, the more the GPU becomes essential. So, oh yeah, then the tensor can also store gradients. So if you print the torch tensor, you might see things like the gradient there. So that happens like when you call the backpropagation depth, and then it'll store the gradient for you. And you need that in order to update your model. So common bugs, so watch out for shapes. So for when using NumPy or PyTorch, I very often will print the shapes, or I'll put in various assertions in my code to check that this shape is equal to that shape, or this shape first dimension must be the same. Because I've caught many errors just by analyzing the shapes of torch or NumPy arrays. Yeah, and then watch out if the data is on CPU versus GPU or NumPy versus torch. Like you can't have like this array plus this array if one is on the CPU, one's on the GPU. If that happens, you'll see an error message with an obvious name, and then that'll keep you informed about what to debug. Now for training models, whenever you're calling something in PyTorch, a very common bug is that even if you're passing in just one data point to a neural network, you need a leading batch dimension. So the first dimension of the input has to be the mini batch size. So mini batch size, like I think we defaulted to like 100 in the homework, but that's for training. At test time, you'll only see like one data point at a time, which means the mini batch size has to be 1. But then when you print the shape, it must say 1 comma whatever the dimension is. So like 1 is the mini batch size. So that's a very important point that is a very common source of mistake. Yeah. Then for training model, the standard procedure is set the gradient to 0 to clear them out. Run backpropagation, so that's you get the loss, and then it's loss dot backward. Take the step in the optimizer, and the optimizer is a more sophisticated version of gradient descent. So it's not going to be like take a gradient, update it based on like one data point. It's going to be a mini batch of them. So like the bigger the mini batch size, like the better the gradient approximation is because you get more information there. Yeah, and again, like this type of procedure is the same thing that you'll have to do. It's very standard. So if you look at tutorials on how to do PyTorch for image classification, you'll see the same procedure. Set gradient to 0, backprop, take step in optimizer. Now, in behavioral cloning, it's very important to know, like, are the actions discrete or are they continuous? Now, in the case of the homework, the actions are continuous. So you're basically doing a regression to predict continuous values. And so the loss function is based on mean square error loss. So that just tells you like how far away are like the vector of your prediction versus the ground truth vector. You take their element-wise differences, square them, and then you average them. All right. Any other implementation tips? Or all of you like PyTorch experts? Are you? I don't know. I mean, yeah. I mean, I'm old enough when TensorFlow 1 was around. That I hated that. No, I didn't hate it. Okay, I'm just joking. Yeah, TensorFlow 1 was very helpful for me to think about this, but PyTorch is a little bit, it's often easier for people to use. Like, even though I found it the same difficulty level as TensorFlow. And again, I think we talked about some similar work at the very beginning of this class. So you might be thinking, well, is imitation learning widely used in robotics? And the answer is, well, yes. I mean, imitation learning very common in robotics research today. So this is a paper from Google robotics team. So it's called Robotics Transformer 1. And you can kind of see from their video that they put in a ton of data. And I mean, yeah, you can see what it said. The last 2 years, I guess I got to speed up a little bit because, yeah. Actually, no, this is pretty good. So one thing that you'll see is that when people have trained things like large language models and other computer vision models, they've had the advantage of training on huge amounts of internet scale data. In robotics, we face the question of, do we have that equivalent internet scale data of physical robot interaction? Do we? But what's easier to get? Is it easier to get a huge amount of text data or a huge amount of robots interacting with an environment? Yeah, text data, yeah. So that's why things like GPT came first instead of whatever people will call GPT for robotic. I don't know. Yeah, so the data text, though, in large language model, you can discover patterns. And same thing with computer vision. You have a lot of internet scale images because people post tons of, stuff online. Like they have images of all sorts of different things. And then in this work, they wanted to create a general robot model that absorbs large amounts of diverse robotics data. Yeah, and then to accomplish that, they had 130,000 episodes, 700 tasks, 13 robots over 17 months of data collection. So this is why robotics research, it's got to be done by companies with a lot of money, not startups. With some exceptions, I should add. But that's why a lot of research is subsidized by the rich companies. I know they've got a huge amount of data. And one thing that is interesting to note is that if you look at their paper, it says, we assume access to a data set. So the notations should hopefully be familiar to you. Like it's a little bit different from what I use because that's the problem with notation, but you can at least see what's going on, right? It says you learn pi using behavioral cloning. And it's citing that 1988 or 89 paper that I presented a few slides ago. Yeah. All right, and then they got all this real world robotics data, and let me speed up the behavioral cloning part. Oh yeah, so the input is language instruction along with images. The output is just directly the action. Like you get the mode, I think that's like gripper, open or close, and then the arm is like the change in the arm, and then the base is you move the base. Because you have a mobile robot, so you have to add in some more degrees of freedom. Yeah. But yeah, I mean, again, key takeaway that lots of data use a simple algorithm like behavioral cloning, and then it seemed to do pretty well. Like the main advantage of this paper is not that it makes a robot that is good for one specific task. It's a robot that's good for many different tasks. Like you give an image, human supplies language command, assuming that it's in distribution, then the robot might do a good job. But the whole point of this paper is to show that imitation learning can scale up when you make the data distribution broad enough. Yeah, and I think we also talked about this earlier. So there's a trend in the robotics research community about trying to obtain and share larger scale robotics data. So instead of having robotics researchers collect a little bit of data for their specific paper or project, and then you write a paper on it, you throw away the data. Here, what they're trying to do is have this massive large-scale data collection among many different labs. Then the hope is, you got this big data, share it to the public, and then other researchers can download the data and then use it along with maybe their own task-specific data, and then train it. And with all this data, your training data distribution is broader. All right, so to summarize, we covered imitation learning. So we talked about behavioral cloning, and then we talked about Dagger. So Dagger, very simple extension of behavioral cloning. In the homework, it is extra credit, but it's also only like 4 or 5 lines of extra code. So coming up next, though, this week we have dynamics, and then the following week we'll talk more about simulators because dynamics are necessary to know like how to simulate robots. So for next Wednesday, be prepared to do a lot of math. So it took me 4 pages of algebra to prepare for that. And then after that there will be special advanced topics. I'll try to talk about, I think, like language and robots is pretty popular. So I'll probably talk about that for a lecture. Then we'll talk about things like a grab bag of topics that we hadn't covered that are important, like what are good 3D data representation, like depth, point cloud, so on, different rotation representation. So I don't think we can go through a robotic class without talking about like good rotation representation. And then I think for the last week of class, we'll just do some final exam practice questions. All right, I will see you Wednesday. I can stick around for a few minutes, but so again, I did say that I cannot do normal office hours today, but I have something going on, but I can at least stick around for a few more minutes since we ended a few minutes early. All right, I'll see you Wednesday then.